Welcome to The Manifest, a podcast all about package management. I'm Andrew Nesbitt.
And I'm Alex Pounds.
And together we're exploring the technical ins and outs of package management, the stories of the people behind the code and the communities around the projects.
Today we're joined by Sam Boyer, lead maintainer of Dep and author of the Go packaging solver GPS. Sam, welcome to The Manifest.
Thank you.
Let's get started by hearing how you found yourself involved in Go, because it's a fairly young language.
Well, really, I love graphs. Somewhere along the line, I discovered that I love graphs, and I started writing graph libraries, and I wrote one in PHP, and then realized that was a terrible idea, and I wanted to find a language that would help me write a graph library that was a little closer to, let's call it, the algorithmic ideal. So I ended up picking Go. It's a whole other story. I now realize that writing graph libraries is mostly a terrible idea most of the time, and that if I really cared about like algorithmic superiority, maybe I wouldn't have picked Go, but it doesn't matter because it got me into Go.
So when we say algorithmic superiority, what do we mean by that?
I mean, whatever the theoretical ideal is for any given algorithm, you can implement it in a way where the language supports that. The Rust zero-cost abstractions type idea, I can make a nice interface for it, but still have sort of theoretical maximums.
And how has Go worked out for you with that?
It actually does pretty well on a lot of things and is good enough that I'm almost never actually worrying about that. And if I really care, then I can write in something else. But most of the time, the things that I appreciate about Go now are much more the things that are often touted about it. It's a language that places value on a certain form of simplicity. This sort of what you see right in front of you is exactly what it is. It reduces some cognitive load in that way at the expense of other things, of course. But it, as the authors argue, does feel like it helps me most of the time to focus on the goal that I'm trying to reach and not the cute abstractions that I could make around it.
Not everyone listening might have had a chance to write some Go or really explored it in depth, but I found it to be a language which has made some pretty unique decisions about how you structure your code and how you interact with it. Could you tell us a little bit more about those specifics and the decisions that are unique to Go?
Sure. So someone else might be able to give a better line-by-line overview of this, but the thing that I've been thinking about as a good example of this recently has to do with a very well-worn argumentative path in the world of Go, which is the fact that Go does not have generics. The effect of this is that you can be very sure that the types that are literally written in the source code in front of you are the types that you're operating on. Sort of nothing is getting slid in outside of your knowledge. You very rarely have to dig in several layers into the code to see what actual types are sort of operating behind the scenes. There's only really one mechanism for doing that, and that's the interface. To be clear, at times I feel very constricted by this. I've often heard it said that Go would be fantastic if I had generics and nobody else did. But we can't have that world. The benefit I'm trying to talk about here is that because we forego the power and the expressiveness that comes from generic systems like this, the benefit that we get is I can simply look at the code in front of me and not need to tear into deep lookup paths to see what actual types are fulfilling an interface or fulfilling a signature. It's much more readily available right in front of me, and for me at least, that reduces cognitive load and helps me to focus on the thing that I'm trying to accomplish.
You initially came to Go because you were looking for something to build your graph library in, and now you are lead maintainer of Dep and also created GPS. So how did you get from A to B?
Yeah, so I have some background doing things related to this. In 2010, I was the lead engineer and architect responsible for moving the Drupal project from CVS to Git. Drupal's code is all self-hosted on Drupal.org, and there were tens of thousands of projects. I think when we migrated, there were maybe like 16,000 or something like that. Distinct projects from people all over the community, and we needed to move those over into Git repositories out of one giant CVS monorepo. The project took about 6 months, but it meant that I had some background with things sort of related to package management at the very least. Got my hands really dirty with Git. Within Go, though, Go has its history of how its package management has worked. It's been spare, perhaps, we could say, since Go 1 was released in 2012. Go-Get is essentially the only official package manager, and it took a few years sort of for the community to agree that this really isn't enough. Finally, I had been working with guys responsible for Glide, one of the major package management efforts that was out there on it, I was sort of getting more and more interested in this problem and considering kind of diving in deep on it around December 2015. And right around then, some discussions started breaking out in the community around where we should go forward with package management. This coincided with the fact that the vendor directory, which is space that the compiler treats specially inside of a Go project structure, it's a place where you can put your dependencies, and the Go compiler will search there before it searches the other places. So it allows you to achieve encapsulation of your dependencies inside of your project. But so this discussion came up, and I basically said, okay, this is a hard problem. And what I saw happening was I saw a bunch of people who had worked on their own tools, a lot of people talking past each other, a lot of people, really well-meaning people, who just had made slightly different decisions, 6 months or a year ago, and that had ended up making it very difficult for them to talk about what they saw as the main problems through the lens of the particular projects that they were working on. I decided that I was going to try to address this by writing a manifesto, because I guess that's what you do in our world. So it took about 6 weeks, and I wrote this giant long essay called "So You Want to Write a Package Manager," in which I try to just sort of describe the whole domain of language package management and what the relevant choices are and the trade-offs and how they interleave with the language that you're writing it for, and the competing concerns, the balance that you have to strike between the mushiness of human requirements and the precision of making things work for computers and reproducibly.
Okay, so let's take a step back a second and hear a little bit more about how you got into computing and your background.
That is actually not irrelevant here. I don't have any formal education in computer science or engineering. I was a medieval studies, international politics, and linguistics major in undergrad, and then I dropped out of a master's program in interdisciplinary program in the social sciences. But I was also engaged in leftist social movements all over the place. And the thing that actually drove me into engineering was I was working with social movements that really, really valued the equal participation of their members. And these were social movements that were like literally spread all over the world. And what I had found was that the communication technologies that they were using really prevented them from being able to realize the goal of horizontal participation. So I was like, all right, fine. I know computers, sort of. Really, I just played video games for years. I didn't really know anything about them. So I'll dive in and I'll figure out how to build platforms to facilitate social structures that these movements say that they want. That's what got me into Drupal, and it goes from there. But I say it's relevant today because I've always been interested in communities, because that's what got me into computing in the first place, and ways of making communities work better together.
And that maps really nicely onto an entry into the world of package management. So let's skip over a little bit of kind of the history of where Go managed to get itself into the mess of package management and look at the future of where Go is going with its package manager. And I guess that's mostly focused around Dep. What kind of decisions have been made around Dep that kind of stand out to you as being interesting or different from other application level package managers?
So first, let me outline how things work today with Go. The only official package manager that we have is what's built into the Go tooling, which is really just one command for the most part. It's go get, and go get works by you give it an address, basically a repository, because, and this is crucial, there is no central registry in the world of Go. You'll say go get github.com/whatever. And if you see Go projects, you'll see a lot of them. The installation instructions are go get, and the address of the project. The Go tooling will then go and clone down that repository, and it will walk down the import paths in that repository, which it can use because in Go, the import paths, most of them look like FQDNs. So it'll walk those down and find the dependencies of that project, and we'll clone those down and dumps them all into one big giant pool that's called the Go path. The thing is, go get essentially just says there is really only one version, and it is the default tip, branch, whatever it's called for the underlying version control system, and that's what it uses. You can also tell go get to update, go get -u, and it will go through and recursively update all of those dependencies in the giant shared pool that is the Go path. So this makes it very difficult to do a number of things. Because the Go path is one big space and you can't have different versions of a given thing on the Go path, it's very difficult to develop multiple projects at the same time if they have shared dependencies, because they're all looking back at Go path. And if they need different versions of them, then what are you going to do? Go switching the version of the thing on Go path? What if that's a repository that actually I was hacking on, because we also hack on the things that are in our Go path? So there's no separation between the things that you are working on and the things that you just happen to depend on inside of Go path. The vendor directory that I mentioned earlier helps with this a lot. It lets us at the very least take things off of Go path and encapsulate them inside of our projects so that we no longer have the multiple projects bouncing into each other. But it sort of induces new problems. Vendor is something that we're very reliant on it now. It's what we're built around now, but it's also something that in the longer term, we hope to be able to move beyond. So, notable design features. One is there is no registry. We just talk directly to version control repositories. This is not ideal, but this is one of those things where Dep cannot make a different decision about this because we need to operate inside of the constraints that the toolchain provides, primarily because the aim is for Dep to move into the toolchain. Can't say merge, it's not going to be a one-to-one thing, but we do want to integrate into the toolchain, and the fewer things that we have which represent departures from the way that the toolchain works now, the easier that process is going to be. So we have a bunch of decisions which break with how the toolchain currently works that we've deferred until after or during that integration time. So registries are one. The other is the nature of names, which is kind of related. But in most systems, the name that you use for whatever your import or require or whatever statement, the meaning is given to that name by a registry. And it's just a string until the tool takes it and hands it over to a registry. The registry is essentially the thing which is operating basically in the role of DNS when you really think about it. Given some input string, it decides what resource that ends up corresponding to. Contrast that with Go, where we have these import paths that, like I said, actually contain GitHub/foo/bar in them. That has meaning. That meaning is given to it by actual DNS. So we have to work on top of that. That also gets really complicated because we have to be able to look at an arbitrary import string and decide how to deal with it without having to consult any external source. We have to do these sort of purely symbolic analysis of strings. And anybody who's ever done that before knows how terrifying that sentence should be. We have to look at an import path and say, this is github.com/foo/bar/baz/bizzle or whatever. And I have to be able to know for any given string where the root of that project is. That's easy enough when it's GitHub, but you can import from anywhere. So how do you deal with that? There are patterned rules around this, but it ends up informing a lot of things.
So the import statements in Go currently allow you to describe the version numbers that are required, or is that specified elsewhere?
Nothing precludes you from doing that. And there is a service out there called gopackage.in, which was created several years ago, that basically facilitates that. Gopackage.in works by being sort of a proxy layer on top of GitHub. A common package that's often imported is gopackage.in/YAML. And that maps to github.com/go-YAML/YAML. But gopackage.in lets you put a suffix on it. So you can say like import gopackage.in/YAML.v2. And what will happen is when GoGet or when Dep talks to the gopackage.in server, gopackage.in proxies the clone of the Git repository through and actually modifies the set of references that Git reports on the fly to only those that correspond to that version number constraint. This is the only place, though, where versions are intermixed with that import statement. That is something that we otherwise try to avoid. And in fact, actually, Dep has entirely re-implemented the behavior of gopackage.in internally. So we never talk to gopackage.in directly because we have to map its model of versioning and constraints onto the model that the Dep imposes on the world.
So if you have two different Go files in the same project that are looking to use a specific Go file from GitHub that are within the same repo, are they able to import two different versions of that same file?
They are not. We do not allow this. We debated this for a long time, and it's something we probably could do, except that it would create a crazy fractal of complexity if we allowed it. It'd be very difficult to understand why it is that you have, some portions of a repository imported at one version, and then other portions imported at a different version, and then that ends up spreading out to the dependencies of that repository as well. And so you have this like split version brain thing happening that infects the entire dep graph.
And that's basically what the Node community has been running on for a long time, where they chose to not make the decision to ensure that everyone is using the same version of the same package within a particular application, which actually kind of lowers the barrier and removes some of those kind of, as I call them, the first and the second levels of dependency hell, preferring instead the kind of seventh or eighth level that you're not going to run into so often, but when you do, it's going to cause some interesting things. Is that a limitation of Go, the language, as well, that kind of enforces that?
It actually is. And so we don't really have much choice about that. It's technically possible with the way that vendor directories work. We could nest in the same way that NPM does, that basically everything gets its own encapsulated copy of the code that it relies on. The problem is the compiler blows up. The names of types are a product of the full path to them. So if I rely on Project Foo and some other project over there relies on Project Foo, but we each have our own copies of it, then instances of types from Foo will be incompatible. And this doesn't always, present a problem, but if I leak out the types from Foo and the other project leaks out the types from Foo and something else is relying on both of them, then when those types from Foo come together, they will be incompatible and the compiler will fail, and there's nothing that you can do about it. So yes, with the way that Go works now, we pretty much have no choice but to flatten up to the topmost level.
At least you do find, the compiler will find those problems for you before you actually deploy those things, right? In the world of JavaScript, you may never know that you are running two different versions of that same thing, and that might be fine. It also might cause some very strange issues. I find it interesting that the NPM community for the longest time decided to kind of go with that trade-off. And it definitely shows in the kind of way that NPM was seen as solving dependency hell, whilst kind of not making a big deal of the subtlety, meant that they could actually kind of push a deeper and deeper dependency tree and actually kind of build up a bigger community over a longer period of time with much more complex dependency trees, because they didn't have to do this collaboration and coordination between different package maintainers. Do you think that has had an impact on the adoption of dependencies within the Go community?
I do. I absolutely do. And yeah, I entirely agree with that assessment of NPM. And to be very clear, like, I believe that this is a trade-off. I don't believe there is a right answer here. And interestingly, it's a trade-off which might be surprising for folks who are not package management nerds, but this is one of those trade-offs which is deeply interlinked with the semantics of the language itself. I think that lack of good dependency management has harmed the Go community in other ways. What we're looking at going forward is some of the trade-off of growth versus, I guess, correctness. Safety is probably a better word, growth versus safety, that are inherent in this. Do we flatten and require just one version, or do we make trees a la NPM? But to my mind, I do think that lack of good dependency management has harmed Go's growth. And I think that either of those scenarios, whether it is tree-based, which, like I said, isn't really feasible for Go right now, or flattening, both of them are better than the historical situation for Go. So incremental improvement either way.
So where did that historical context come from? Because they must have seemed like good ideas at the time.
I think there are a few things there. The reality is, though, that when they were originally working on all of this, Go was first announced, I think, in like November 2000. 2009. I really hope I get that right. And then, Go 1 released in 2012, I think. And there were a couple things going on. These ideas were more nascent then. Yes, NPM existed. Yes, Bundler existed. But part of it, I think, is the static versus dynamic language divide. Part of it as well is, there's this Go on compatibility guarantee, which promises that the standard library, at the very least, will not have backwards incompatible changes. And they have a semi-formal definition of that, which actually we are turning into a more formal definition and putting into a tool that will use, similar to how Elm package works, will tell you what your next Semver release should be. So we are codifying what Semver means in the context of Go. So yeah, I think they were focused on this sort of compatibility guarantee that they had within the standard library. There's also just the basic fact that the folks who were designing it work at Google, and Google has a large monorepository. They don't, just on a day-to-day basis, have to deal with these kinds of problems. So it wasn't something that was necessarily a felt experience for them. I can't blame anyone for not having those things pressing on their lives all day. So from there, I think what ended up happening was, we had a couple of years of, all right, we need to really try to sort of make these things work, and a bunch of arguments got interlaced with this, right? Like, Go is a simple language, and don't write it backwards in compatible code, and a bunch of the things that are really positive about Go ended up sort of being brought up as cultural approaches to countering the deficiencies in the package management situation. What's really interesting now is that I firmly believe that the Go community has built a lot of culture around things like not making backwards incompatible changes, which I don't care how good your package manager is, like, that's always a complicated situation. So I am kind of happy that we have this past that we've had, because now going into this era where we have better package management, we still have a lot of the residue of this culture that will help us be better stewards of our ecosystem, even when we have tools that let us be a lot lazier.
So Go is a compiled language, and it's also a static language. Do those two elements have any implications for how it does package management?
Yes, it does. It definitely does have an impact on how we do package management. I'll talk about the compiled aspect first, because that is the easier sort of and more obvious one. Whereas a dynamic language needs the dependencies to be present in order to actually, run, which means that you are npm installing or composer installing on your production boxes. Go as a compiled language. It means that the last place that you actually need to collect your dependencies into place is in your build box. Go is all about the statically linked binaries. You just chuck that thing in production and you're done. Nothing really jumps to mind, though, as a terribly big difference in terms of how we do the rest of our work, just because it's compiled. However, being statically typed is really interesting. I'm really interested in doing on-the-fly type analysis in much the same way that a compiler does to determine whether or not versions are compatible. This is something that I was much more hopeful about maybe last year. I thought that we could do a lot more with it. As I've looked into it more, I've realized that it's not feasible, even in a language with a very simple type system like Go's. It's not feasible to sort of prove everything all the way down. But I have this hope sort of growing in the back of my mind that we can create a complementary system that exists alongside versions and version constraints and Semver and all of that, which are actually doing the checking on the fly to see, oh no, you can't actually use this dependency at this version, even though your constraints say that you can, because we can look and see that you are trying to access a field on a struct that doesn't actually exist in that version. We cannot say that code is compatible, but we can say that it is incompatible.
So that's quite an interesting aspect that could be brought back into the discovery side of the package management, which I guess Go has punted on that mostly out to say GitHub can solve this, and you find your projects by just searching for Go projects on GitHub or Bitbucket. One thing that you might be able to do with a system like that would be able to introspect each version of each package and its dependencies, and basically be able to knock out all of the incompatible packages that essentially wouldn't be able to build a tree, potentially reducing the amount of dead packages or packages that are incompatible with other ones that you know to be in your dependency tree already, and actually reduce down to, here are some good, probably known working versions of things that you'd be able to use. Could you imagine that being a tool that would essentially index and connect the dots between every different Go package?
Yes, I absolutely think that's something that we can do. I designed GPS around the idea that all of the work that it's doing right now to extract information from source code, to feed it into the solver that's making decisions about what things work together. I designed it around the idea that we could incrementally push those responsibilities towards the edge, cache them, something, whatever. The point is, yes, like right now we do almost all of the work locally. And if we develop registries where we can trust that they've done some of the work already, then we can reuse that work. We can avoid having to explore a whole bunch of already known to be incompatible versions. We don't have to do relatively expensive type compatibility analysis because it can be done once and then just look it up.
You could even potentially go as far as pre-compiling or at least collecting sections of that dependency tree, especially if you know that it doesn't clash with any other pieces of the dependency tree of the whole application, to kind of save doing that recursive resolving over and over.
Yeah, it does get tricky because it's graphs, man, and graphs are snaky. I've thought some way down these paths. I haven't sort of gone all the way down them because we have plenty of work right in front of us to do. But a core idea in Dep is this notion of a sync-based tool, which is to say that we think about there being a few discrete different states that we want to synchronize between. There are basically four states. There is your project code itself. There is your manifest type file where you express constraints. There is your lock type file, which is the fully transitively resolved snapshot of your build. And then there's the space where your actual dependencies are stored. Again, source code. The goal of being sync-based as a design philosophy is that the tool should always seek to exit where all four of these states are in sync, are correct with respect to some function that defines a relationship between them. The hardest part of that tends to be, for some languages at least, is mapping the project code onto the lock file. For Go, it's easy because we have fast static analysis and we have unambiguous names that we have to work with. So we can just keep all this stuff in sync all the time. The reason that the relationship between the different states matters and the function that maps project and manifest to lock matters is in Dep, what we do is we take a hash of all of the inputs. That is all your import statements, all of your constraints, all of the information that is relevant to constituting a lock, and we hash it. And we have a SHA-256 hash digest, which sits in your lock file. And that information can interestingly be used potentially as a key that we could fire off to remote servers. I've done some work. I've worked some things out. For these inputs at this time, this was a good solution. This one worked.
So interestingly, I've done a similar thing with the libraries IO database, where as I've indexed every version of everything, and Go being slightly weird, not having discrete versions currently doesn't work with this implementation, but for most package managers have that kind of published discrete version that can't be easily changed or like the code replaced in the sense of a git force push to a particular tag. Because I have the timestamps for those release dates of all of the versions, I've written a kind of poor man's dependency resolver that you can actually pass a date, which will scope the SQL queries that it runs against Postgres as it does a recursive resolving, to be able to say, can you give me the dependency tree back on this date? So you can actually roll back in time and say, I'd like you to get me that dependency tree back last week because I don't have the lock file to be able to produce what was there. And for some package managers that don't have lock files, that's really useful. The R package manager doesn't actually have the ability to set an upper bound on version numbers when declaring a version range. So if someone publishes a newer version that you don't want, you actually can't say, no, I don't want to install that version. I want the previous one. The solution to that is that they take a snapshot of their registry every day. And actually, you can then say, I will point my package manager at last week's registry and I will get exactly back what I want. The nice thing about doing that is that at least you can say, I've frozen the world, and I can be sure that every time I resolve this, and any caching that I do around this will be identical every time.
That's fascinating on multiple levels. One, simply because by precluding the possibility of specifying an upper bound on ranges, you can avoid satisfiability, which is interesting. I'm thinking about this now, though, as a thing that we can do, at least for reconstructive purposes, and how much it would take to make Dep operate in that way. It actually wouldn't be that hard. With the way that our system works, we could pass in basically just a date to the master object, the source manager, which works with all of the upstream repositories, and say, don't allow any versions newer than this date, and it would work.
Yeah. Assuming that no one has changed those repositories since that point, the force push is always going to cause you pain where you just say, I hope that this mutable file system over there hasn't changed since the last time that I asked for it.
This is a nice segue into one of the questions that I had, in that lacking a centralized repository and a centralized place where there is a canonical package, it seems like Go might be more vulnerable to things like history in a Git repo being rewritten, or a Git repo completely going away, or something else changing underneath. Have there been problems with that in Go?
Yes, and guarding against some of those issues is probably doubled my development time last year when working on GPS. So there's the left pad problem. Upstream project just goes away. So there's some split in the Go community as to whether or not you should commit your vendor directory into your project or not. Really, the main reason to do it, and this will always be a reason to do it, is because you're immune from left pad if you do. You've got a copy of the code locally. You can survive without the upstream. Dep actually does not work well with that right now. Dep really sort of does continue to require the upstream to be present. We treat vendor as dead code. So you can have something in there, but if it's gone away upstream, then Dep will blow up. Tags moving, though, is definitely something that we had to accommodate from the beginning. And when I approached this, I designed a system for versions that was sort of centrally designed around Git, but is equally applicable to the 4 version control systems that we have to support, because that's what GoGet already supports, and that is Git, Mercurial, Bazaar, and Subversion. That version system has 4 types in it. So you've got semantic versions, which correspond to, they have to be tags in the Git sense, and then they have to actually conform to the shape that is specified by Semver. There can be branches, which are any, whatever underlying constraints are imposed by the version control system are the boundaries there. And then you can have these plain tags, which again, like a Git tag, which doesn't match with Semver. But the semantics that we assign to them are that. So there's branches, which are references that we expect to move. It is a normal thing for them to move. And by move, I mean they correspond to a different underlying revision. The other piece of this is that all 3 of Semver, branch, and plain tag are assumed to have, or it is possible to pair them with exactly one underlying revision. And then revisions are something which are immutable. And that is true for at least all 4 of those systems that we have to work with. There is an immutable revision that we can get out of them. So we expect that branches move, and we accept that it is possible that either Semver or plain tags would move, even though we don't really, even though it's frowned upon, it's entirely possible. The system cannot break if it happens. Functionally, we treat these mostly the same. We index everything by revision, and then we have a map on top of that, which are the plain, Semver, or branch that correspond to those revisions. And when they move, really the only functional difference is if it's a branch, well, it's normal for it to move. If it's one of the tag types that moved, then that's something that we would produce a warning about, or would ideally, but I don't think we currently do. But yeah, we definitely had to architect around this from the very beginning, because we don't have something like a registry to provide us a guarantee like Crates does that it's immutable and append only. It's one of the properties that I really, really want to have in a registry.
It also seems like Go could be vulnerable to some kind of impersonation attacks as well. One thing we've seen with other package managers is malicious packages being published which have names very close to an official package name and hoping that people fat finger it. But in Go, it seems like you could have a package with the same package name, just a different repository path. On GitHub, that would be from a different owner, but anyone can publish their own Git repo. Has that been an issue?
Not to my knowledge. So there's different degrees of impersonation, right? Like, sure, there's fat fingering over and accidentally getting a malicious package. And we don't have any defense against that right now. Because there is no canonicality, how would we even know that you fat fingered? Like, we can't help you defend against that. What we do have, or are working on now anyway, is we have an additional layer of hashing that we do on dependent source code. So over and above the SHA-1 that we pull from Git, there is a SHA-256 hash digest, which will go into the lock file, which identifies the Go code. And we can do that for any of the 4 different backends. And we're ultimately going to use that for a bunch more things. That, at the very least, helps with attacks where, if someone is somehow intercepted, like if you're using a proxy or something like that, if someone has attacked your company's proxy and they've stuck a false Git repository into there, as long as someone had a good version of whatever upstream project was there before the attack, then those hashes won't match and everything will blow up and everything will stop. But as long as we're in the domain of like, what is the right project to grab? Yeah, there's not a lot we can do about that. But maybe I've misunderstood the problem you were posing.
No, that is the problem I was posing. And it was less a question of what does Go do to fix this, because there may not be things that you can do to fix it. I was more just asking, has it come up?
Yeah, no, it's well, and I think part of what I'm saying is, how would we even know if it did?
That's a lot more scarier question. You have that in compilers as well, right? Where how do you know that the compiler that was compiled with a different compiler didn't compile something horrible into that compiler? You need a full chain of provenance to be able to prove where everything came from. At least Go is downloading the source code and not downloading binaries. It's actually like at least right there to be able to introspect it before you work on it and be able to see everything that's going into it. But yeah, you're always going to be relying on, at some point, I downloaded something from the internet. I should probably review this, or at least have some way to look at other people's previous reviews to make sure that that is what is expected. But I get the feeling that that's kind of hasn't really been solved by any package manager community, at least at the application level. The system level, people have a much better grasp on that, but they're also dealing with a lot more binaries and precompiled things from different sources that they need to be able to prove that's actually came from where we expect it came from.
Well, and this is where we get into, are you going to sign your releases? And whose signatures do we trust? And it becomes much more of a human problem. And I think the other factor of why it is more feasible, perhaps, for system package managers to take steps like that, whether they do or not, or whether they do them well or not, is because the community of people who are working on putting together overall a set of packages that constitute an overall release for Ubuntu or whatever, they know each other. It's a finite group. They can do things like sign each other's keys and actually attach signatures to these. And it's possible to know like all of the signatures that you should trust for a given release of Ubuntu, which you can then use to verify the packages that you get on the other side. But because language communities are pretty much by definition open and not finite, you have this just constant problem of like, which all people do I trust? It's much harder to implement a solution of that shape.
One thing you mentioned earlier was satisfiability. What is satisfiability and how does it relate to package management?
Satisfiability is a general problem in math and computer science. It is NP-complete, is the first problem that was proven to be NP-complete. It's one of CARP's original 21 NP-complete problems. I like to refer to it as the original gangster of NP-complete problems because you can sort of reduce everything to SAT. Indeed, one of the things that's interesting about SAT solvers, Boolean satisfiability solvers is that because you can reduce everything to them and because they are this nice sort of general way of expressing these constraint problems, in general, what they're doing is I have a whole bunch of different propositions. Can I find an assignment for all of the variables that will evaluate to true for all of the propositions? But because you can reduce all these different problems to them, SAT solvers are very useful because you can write a general SAT solver, and in theory, at least, it can solve problems in a whole ton of different domains. Everything from, like weather prediction to problems in AI to version selection. Indeed, the problem of version selection, that is figuring out, and I can put a narrative spin on this one more easily, as long as you have the requirements that, one, we want exactly one version of any given project in our dependency graph. Two, we want to honor all of the constraints expressed by all of the different projects in the dependency graph, including any situation where you have multiple things depending upon one dependency. And then there's, a bunch of versions of these individual ones that we might try. Then we get into a situation where we need to potentially search this very large combinatorial space of different versions and different constraints in order to try to find an overall dependency graph where all of the different constraints are satisfied and all the different required packages are present in the graph, and there is exactly one version of each of them. It's a knotty problem.
So we talked a little bit about a number of complicated mathematical and computer science problems that go into package management. How did you go about researching and learning about these different things?
Yeah, so I started looking at this a number of months ago. Really, what interested me was that given that SAT is NP-complete, given that NP-complete problems are generally terrible problems, which any decent engineer should look at an NP-complete problem, and the first reaction to that is, well, I'm not solving that. How do we get around this? The question to me was, how is it that we have so many different projects that are out there for solving problems more or less like this, both at the system package management level and at the language level? How is it not more terrible? This problem is terrible. Like, why is everything not burning down around us all the time? Which is a real question. Like, these problems are NP-complete. People don't even necessarily know that the problem that they're solving is NP-complete. Why isn't everything broken all the time? So I started, looking at Minisat, which is a sort of entry-level gateway project in the world of satisfiability, which is its own little interesting subculture of computer science. But Minisat is designed to really be sort of as simple as possible of a solver, but still a very highly effective one, such that you can get in and get your hands dirty and start understanding how some of these basic satisfiability algorithms work. And I started trying to do that, but eventually I realized that the problem that I was having was that I did not have, like, sure, I can go read about horn clauses all day, but I'm not going to be able to get my head around what it is that is perhaps so much more powerful about these generic SAT solvers versus what it is that we have today. So I went out and I bought Donald Knuth's The Art of Computer Programming, Volume 4, Fascicle 6 on satisfiability, and I actually read it, or at least most of it, enough of it, to try to figure out what was going on. Why aren't things more terrible, like I said? So I came to some interesting conclusions. So the way that satisfiability usually gets talked about, at least sort of from my perspective, it feels like, we talk about SAT solvers as these amazing mythical things that have magical powers for solving this horribly hard problem. But the thing is that it's not just like you can take some problem that you have that exists in some domain over here and have it magically fed to the SAT solver. No, you need to actually take your problem and figure out how to encode it in a way that the SAT solver can read. And this is more or less a straight quote from Knuth right now. There is at least as much art and complexity in the process of encoding SAT as there is in actually solving SAT. And once I read that, I was like, okay, everything makes sense now. Because Boolean algebra is sparse. You've just got true and false and then clauses that stack up on top of each other. So pretty obviously, if you're going to take a domain which is as complex and has as many different types of sort of constraints and overlapping concepts as version selection, then you're going to have to do a whole lot of translation and remodeling of that problem in order to feed it to a SAT solver in a way that it will recognize. So the thing that I learned is that part of the reason that SAT research is so difficult, and that fully general SAT solving is so difficult, is indeed because solving on that incredibly sparse input makes it very, very difficult to know what sort of patterns you might look for in order to take advantage of patterns and structures in the data. The general solvers have to sort of figure out what the patterns are as they're going in order to figure out what the right algorithm is to apply. Many industrial SAT solvers actually employ multiple different strategies and will sometimes dynamically pick different strategies depending on what they've seen from the inputs so far. So now a little history. In the late 90s, the technique for fully general SAT solvers was discovered. It's referred to as conflict-driven clause learning. And this was basically the difference between SAT being a ridiculous problem that no one could ever solve and suddenly like, oh, wait, this is like useful for industry now, once CDCL solvers were discovered. And when I started reading about the basic way that CDCL solvers work, they have a concept of a trail and later discovered notions of back jumping. And then they have this sort of bounded model checking stuff that's going on in there as well. I'm like, oh my God, I have all of these things in my solver, but I didn't have to think about them because these are just things that make sense inside of the domain of package management. Once we get out of this incredibly just abstracted thing that are Boolean proposition clauses, and we move back to the richer environment that is, I have projects and they have versions and they have dependencies and they have constraints. There are relatively obvious steps that an implementer can take in order to solve the problem much more efficiently that are much harder to see in the abstracted context. In fact, the notion of backjumping, which is essentially when a solver encounters an irreconcilable conflict, it has to decide what to do next. If I'm trying to pull in project A and then I've already pulled in project B and project B has a dependency on project C and A also has a dependency on C, and I see that the constraints that A and B declare on C are disjoint. There's no way that we could ever find something that would satisfy both of them. I have to decide what to do next. So backjumping in general says, given that we've encountered a failure at this point, instead of just sort of blindly backtracking to the next choice that we could make, we're going to back jump to the last known failure point. It's a sort of smarter backtrack that knows the next place that is likely to have, that even could possibly have a resolution. So that notion, fairly obvious when you're looking at things in the richness of the domain of real versions. It took an entire dissertation to come up with the notion of backjumping in the context of CDCL solvers in this totally abstracted domain. So this is my basic answer. The reason why we have managed to do relatively well with this is because it's quite possible, it seems, for engineers who are more or less following their noses to come up with algorithms that strongly approximate the way that CDCL solvers work. They're just domain specific. And CDCL solvers are very powerful. They have, sort of known failure modes, and there are issues with that, but it's totally possible to write a domain-specific CDCL solver for this problem that we have right here in front of us without having the mathematical background or even knowing that that's what you're doing or even knowing that CDCL solvers are a thing.
So what you're saying is anyone could build a package manager without any of this previous knowledge and kind of accidentally end up in the right place.
I mean, I think there's certainly plenty of places that you could go wrong, but yeah, that seems to be the case.
Yeah, it's not literally that could happen, but that has happened repeatedly in every language.
Yes, over and over again.
So looking around at the decisions and architectures of other package managers, are there any of those things that you look upon with envy and that you wish you had in the Go world?
Yes, there are a few. I really want Cargo's Yanks a lot, and that's something that we just can't have without registries.
Tell us about Yanks. What's a Yank?
Yeah, sorry. So Cargo allows you to yank a version. Crates being immutable and append only, you can't, delete something off of it, but you can yank it. I haven't actually seen the code for this. This is my understanding of how it works. When it's going through and trying to pick versions, it will see that a given version has been yanked, and it will not consider that in any new solves that are going through. However, like if you currently have a version that's been yanked in your lock, then it's at least possible that it would remain in your lock until you explicitly choose to move it. But once you move away from it, you can't get back there. So it's a way of pulling versions that are known bad or have security problems without causing immediate downstream chaos because the version is just gone. We can differentiate between something that should no longer be used and something that perhaps never existed at all. And how did you have that thing in your lock file in the first place? Why were you editing your lock file? That's not what you do.
Yeah, that exists in RubyGems as well. So rubygems.org I'm not exactly sure when it came in, but it's definitely a gem cutter, like new version of rubygems.org that had that. And it was the kind of reaction to people asking for code to be removed and the fallouts of that being incredibly painful in particular situations actually reduced their amount of support requests that they were getting massively. And a really good way of saying like, okay, well, you can stop people downloading this, but if they're going to specifically ask for that version, it's still going to be available. And if you really, really want to remove it, you're going to have to send us a DCMA takedown request to actually yank that thing, which whenever you look at these kind of immutable systems, they still need to actually be able to follow the laws of the countries that they're based in, which often means that code should never have been there in the first place, even if there are many people that depend on that. It may have to go, but the yank is kind of a nice middle ground and allows the users to work on it themselves without having to have some admin person kind of be the ruler and the decision maker around a particular package manager, which happens in some, and others kind of still manage to have a registry without needing kind of a gatekeeper.
Yeah, that whole class of things you just described is one of the biggest set of concerns that folks in the Go community have brought up about introducing a registry. Access control and having people who sort of lord this thing or that thing over who controls it. I mean, all those sorts of questions, which inevitably get complicated, and yanks are just great on every level. But as you say, not a replacement for deletion. There are still cases for that, but we just don't want deletion to be the normal workflow.
So if people want to learn more about Go, Dep, and GPS, where should they go?
So the main place to go is github.com/golang/dep. We conduct most of our development just by issues. We do have a mailing list. It's not that well trafficked. Unfortunately, I'm not great at managing contributions via mailing list. But we also then have a Slack channel in the Gophers Slack, the vendor channel, where we are very friendly and present and happy to answer questions and provide guidance to folks. I also have been writing periodic updates on Dep, cheekily called Dep status, since that is a command that you can run. Those are all at sdboyer.io/Dep status.
Great. Thanks so much for coming on and sharing some of the more technical details and the low-level problems involved in package management. It's been really interesting.
It's been wonderful. I rarely get to nerd out on things like this. I really enjoyed it.
And that wraps everything up for this episode of The Manifest. Next time, we'll be talking to somebody new and exploring more of these package nerdery things. Bye for now.